the little prince is sitting on his little planet, and he's watching the planets go by, and so suddenly he's seeing 3 of them. 1, 2, 3. And he wonders, what would the center of mass of these 3 planets be? So let's calculate it. We have one planet here that's 3 times the mass of this guy, and then this one has half of m1. And I've written this up there already. And the center of mass, when we want to determine its coordinate, it is a coordinate that depends on this coordinate system and this origin here, then we need to have the total mass of the system because it's a mass-weighted coordinate. And so the total mass is going to be 4.5 m1. And if we want to calculate this this position function of the center of mass, RCM, that is the mass weight here. And then we need the sum of all our masses times our distances. We're going to sum here over j from 1 to n. And what that means is we need to now write out the sum for our 3 planets. And we need to give this a radius here, so the R1 would be going from here to here, R2 goes from here to there, and R3 from here to here. We need to write them out in the I hat direction and in the j hat direction. Let's add that here. And then sum it all up and calculate our R. So let's write this out. We have m1, and we're going to have 35 and 10. 35 I hat plus 10 j hat plus m2. That's going to be 5 and 20. 5 and 20. And then m3, we have 40 and 30. And what we can do, and of course that has to be divided by my system mass. And what we can do is we can concentrate first on the x component and then on the y component. And maybe we'll just continue here. So we're going to have, and we can plug in all the m's. We'll do for the x component first. We're going to have m1, and then we have 35 I hat plus, here we're going to have half, m2, that is 3, m1, 5, plus, and for m3, we have 0.5, m1, 40. That's in the I hat direction. And we'll have to divide that over our system mass, and then we do the same for the y component. So m1 10 plus 3 m1 20 plus 0.5 m1 30 j hat. And again, we have to divide this over our system mass. So this boils down to, hang on, let me redo this again. Let me actually look at the answer first. What do I have here? 70 and 85. Okay. So this boils to m1 over the system mass, and we have 70 in the I hat plus 85 in the j hat direction. So the 70 comes from this term, the 80 comes from this, and I put it back together, and now we need to plug in this one here. And so we will get in the end that RCM equals m over 4.5 m. So the m goes away, and we have a factor of 1 over 4.5 here. We'll divide this through, and we're going to have 15.5 15.5 in the I hat direction and 18.9 in the j hat direction. All right, so let's see where this fits on our graph here. So 15 in the I hat is somewhere here, and 19 is almost 20, so it's going to be here. So about there. So this is my RCM, and this here is my center of mass of the system of these 3 little planets. Of course, we used approximate masses here for the planets, but if we look at the real numbers, imagine that this would be Earth, and it has 1 Earth mass. And if this was Saturn, it would have something like 318 Earth masses. And if this is Pluto, it would have 0.0025 Earth masses. You will see that Saturn really holds all the weight. And if we were to do this calculation with these numbers here, then our RCM would, and keeping this coordinate system in the arrangement of the planets, then it would go right into, if here's the center, it would go right next to the center, right over here, because Saturn just weighs so much more than Pluto and Earth together.
So now we want to find the center of mass of a uniform rod, and we have the result for a continuous body, which is an integral over the body of dmr to that mass element dm divided by an integral of dm. Now our goal is to figure out how to apply this result specifically to real physical objects. And the key, as always, is choosing a coordinate system. So now I'll draw the object again, and the first thing I'll do is choose an origin. I can pick my origin anywhere I want. I could pick it in the middle, I could put it in the middle, I could put it at this end, I could put it at that end, I could put it down here, but I'll choose it over here. Because the object is linear, this is a very Cartesian system, I'm only doing a one-dimensional object, so I choose my coordinate system plus x. That's step 1. Now, my origin. Now, here comes the crucial thing. In this argument, dm is the infinitesimal mass element. And I want to pick that at an arbitrary place in the object. I don't want to pick it at the origin. I don't want to pick it at the end. Note down here, this is x equals L. So I'll arbitrarily pick an infinitesimal element. I'll shade it in dm. That represents, this is what I'm going to make my summation over when I do my integral. I'm going to add up all these dm's. And the point is that the dm's are different distances from the origin. So the vector, and here's the next step, is I draw a picture of my vector rdm. So now I have these terms at least explained in my diagram. The next step is to introduce an integration variable for both of these quantities. So step 1 was the coordinate system. Step 2 was the identification of dm. And step 3, and I think this is absolutely the crucial one, is to introduce the integration variable. Now, you'll see that will come in 2 different places. So this is the quantity, the distance from dm to the origin that's changing. You can see for each of these little elements, that changes. So what I'll write dm as a vector is x prime, which will be my integration variable in the I hat direction. So the integration variable is x prime. That's the first place that I introduce the integration variable. And x prime, you can see, will vary And it varies from x prime equals 0 to x prime equals L. And that will show up in terms of the limits of my integral. Now, the second place that the integration variable comes in is dm. I want to express dm in terms of x prime, which is a measure of where this object is. And that's how, if we choose this length here to be dx prime, notice in terms of the integration variable, then I have a relationship between dm and dx prime. dm is mass in this little element. dx prime is the length of the element. And if the whole object is a uniform rod with a mass capital M and a length L, then it's just given by m over L dx prime. And this quantity, m over L, is an example of a mass, linear mass density, which we have a skill challenge about. So I have two places where my integration variable has been introduced. And now I can write up every piece in this integral. So let's now indicate that we're integrating from x prime equals 0 to x prime equals L. dm is m over L dx prime. And our vector is x prime I hat. And downstairs, it's just m over L dx prime from x prime equals 0 to x prime equals L. And that's how I set up the integral for the center of mass. Both of these integrals are now not difficult to do. Notice it's x prime dx prime. So this integral is x squared over 2. And I get 1/2 m over L, L squared. And downstairs, dx prime from 0 to L is just L. So the downstairs integral is just m over L. And when you have m over L's cancel, we just are left with this is just m, not m over L, dimensionally incorrect. So we get, for the position of the center of mass, the m's cancel, one of the l's cancel, and we have an I hat in this expression. So our answer is r equals L over 2 I hat, which is exactly what we expected. We expected the center of mass to be halfway down the rod.